now we move to the introduction of Gauss law, having understood what the electric flux is, and in particular how to calculate the electric flux through a closed surface, and what are the properties of the electric field through a closed surface. It might be positive, it might be negative, it might be zero, depending on the net number of field lines crossing that surface. So this is a crucial observation, because as we will see, Gauss law actually is based on such an observation. It tries to explain this behavior of the electric field lines. Gauss law, what it is, it's a relation that expresses a relation between the net electric flux through a closed surface that we have seen how to calculate, and the electric charge enclosed by that surface. Now, this surface, the closed surface where you apply Gauss law, is called the Gaussian surface. This term is crucial, and it will come up all the time during the analysis, and we have to internalize it and understand. The Gaussian surface is generally a hypothetical surface that you imagine, and to apply Gauss law to it. Okay, it can be any surface, but it is a closed surface, and at some cases it might coincide with a physical surface, sometimes it might not. The issue is that it is the imaginary surface that you create in order to apply Gauss law to. Now, Gauss law says the following. It says that the net flux through any closed surface, that's a Gaussian surface, surrounding net charge Q is given by Q over epsilon naught and is independent of the shape of that surface. So it says net flux on one side, there is the flux generated by through a closed surface, generated by finding the integral, the surface integral of the electric field at the surface over the whole surface. This is the left-hand side of Gauss law, and it's equal to this flux. If you calculate this integral, it will give you just merely Q over epsilon naught. The net charge, Q, is the net charge, the sum of all positive and negative charges enclosed by the closed surface. And this result is true irrespective of the shape or the size of that surface. So let's do it for some familiar surface. Assume that I have this surface, okay, this point charge. I imagine a surface surrounding that charge. Here I'm just taking it as a sphere, although this is not necessary. And then there is an electric field at the surface here. I evaluate the flux of this electric field, but just as I have learned, by carrying out this integral. This is the left-hand side of Gauss law, saying if you evaluate this integral, find this flux by evaluating this integral at the surface, the result that you get is numerically equal to the just simply the charge enclosed by the surface divided by epsilon naught. So this whole complicated thing boils down to charge inside the surface divided by epsilon naught. Now this is quite a remarkable relation, and because it tells you, well, if you know the charge inside enclosed by a surface, then to find the flux, if this is your target, you just sum all the charges and find the net charge divided by epsilon naught. Don't do this integral. This is what does it tell me. Okay, so that's the relation, and this result doesn't depend on the surface, the shape of the surface. This surface can be anything of any shape. Now, to appreciate probably why is this so, of course, we might look at this figure and remind ourselves that when we introduced the electric field lines, we said that the electric charges are actually are the sources of the electric field lines and the sinks of the electric field lines. Yani electric field lines originate and terminate at electric charges. So for example, in this example, I have this surface, arbitrary surface, and I have only a single point charge inside this surface. Now, evidently, the flux through this surface, which is the net number of lines crossing this surface, will be determined only by the number of lines coming out of this charge. The larger the charge, you will have a more number of lines coming out of the surface, and so you will have a net flux, for example, a larger flux. The smaller the charge, you will have a smaller number of lines, so you'll have a smaller positive flux. You remember positive flux when you have net number of lines going out of the closed surface. Now, if this were negative, in this case you would have field lines would be coming into the surface, and in this case you will have a negative flux through that surface, and this negative flux will be determined solely by the charge, which is negative in this case inside the surface. So this is just, it's not a proof, it's just a way of making this fact that the flux actually is determined solely by the charges to make it plausible for you. We will try to make Gauss law plausible by considering another quantitative example shortly. Of course, a formal proof of Gauss law exists, but it is evidently beyond the scope of this course. Now let's consider an example to illustrate what do we mean. We have a single point charge here, and we have several surfaces, S1, S2, S3, enclosing this charge. Now, S1 is the only regular surface, which is a sphere. The other surfaces are quite irregular. Now, the net flux, according to Gauss law, the net flux through all these surfaces is the same. Okay, this is what does Gauss law. Although the electric field at the surfaces varies, because at different points here, this surface here, the electric field, while it might be constant at this surface, but for this surface, the electric field will be irregular. It's different than what it is here. Here, the electric field at this surface will be irregular, also will not be constant, and it will be different than this surface, but the flux will be the same, and it will be solely given by Q, which is the net charge, divided by epsilon naught. This is what Gauss law says. The idea here might be the fact that the electric force goes as 1 over r square actually, and it's probably a place where I just can hint on what I have mentioned at the beginning, that Gauss law is actually a consequence of the fact that electric force goes 1 over r square. Why is this? Here, for example, this is a smaller surface, and the electric field here is stronger. Okay, so this flux is roughly the area multiplied by the electric field. Now, as you go here, the electric field becomes weaker, but it becomes weaker by 1 over r square because it drops as 1 over r square. But the surface area, when you go away, okay, drops also, like increases by r square. So the product of the r square cancel each other, and the net flux remains the same, because the flux is E times area. E drops by 1 over r square, the area increases by r square as you go away, and so the net flux remains the same. This is just it's not a proof, it's just explanation, some rough explanation of the fact that the Gauss law is a consequence of the 1 over r square behavior of the electric force. Now let's prove, or actually more precisely demonstrate, that Gauss law is true quantitatively by considering a specific example. Our example will be a single electric charge, positive charge, and we will consider as our Gaussian surface a sphere centered at the charge. Now, by demonstrating Gauss law, we are going to do the following. We are going to calculate the left-hand side of Gauss law, this, for the sphere, okay? So calculate the integral, finding the flux by calculating the integral, and verify that our results is just the charge enclosed divided by epsilon naught. Okay? Now, we are doing this for very special cases. Point charge at the center of a spherical surface, which is our Gaussian surface that we take. Okay. Now, I know that the magnitude of the electric field of a point charge is just kq over r square. What does this mean? It means that the magnitude of the electric field at the surface is constant of the sphere, is constant. The direction, we know that the electric field of a point charge is along r hat. R hat is a vector that goes from the source to the point where you want to find the field. So it is radial. So and the normal to the surface of a sphere is also in this direction. So actually r hat, the direction of the electric field, in other words, and delta A that we use in Gauss law are parallel. And this applies for all delta A's on the sphere. Okay? So the electric field is now uniform. It's constant on the whole sphere as a magnitude. Sorry, not uniform. The magnitude of the electric field is uniform on the surface. The direction of the electric field at all points on the surface is parallel to delta A. Okay? And therefore, when you do this, you start calculating the flux. So you have to take E dot dA. Now, the angle, because E and dA are always parallel for all dA, you can just replace this by E dA, because cosine theta is cosine 0 for all dAs, and cosine 0 is 1. So it reduces E dA. The second thing, you can take E outside the integral. Why? Because it is, you are here calculating the integral at the surface. And at the surface, the electric field is just a constant, doesn't vary. So, you know, when you have an integration and you have a constant that doesn't vary over the interval of integration, you can take it outside the integral. And so you take E outside. So this, when you calculate the flux, this quantity reduces to this. It is E, a constant that I know what it is, multiplied by this summation, which is dA. Okay? Now, of course, I just forgot to say that when we consider closed surfaces, I just remind you that we have this square. Sometimes it is a circle, just to remind us that we are talking about a closed surface here. So A multiplied by this integral. What is this? This is the integral of dA. What is the integral of dA? The magnitude of the dAs, actually, the magnitudes of the areas. It tells you sum over all these area elements. But what does summing over all these small area elements that cover the sphere means in this case? It means find the surface area of the sphere. And we know what is the surface area of the sphere. So since it is just 4 pi r square, E is kq over r square. This r square cancels this r square, and you get this expression for the flux. Now, k is 1 over 4 pi epsilon naught, if you remember. If you just substitute it, you get the right-hand side of Gauss law, or the flux equal to q over epsilon naught, which is exactly what does Gauss law says. Gauss law says the flux is, when you calculate it, you should get it numerically equal to the charge inside the surface divided by epsilon naught, and this is exactly what you get. So we have now verified Gauss law for the special case of a point charge inside the surface, surface, and this surface, which is our Gaussian surface in this case, is a spherical surface centered at the point charge. This is not a proof. This is just a general. It's not a general proof. It is just a demonstration of Gauss law. Now, try this checkpoint before you proceed to some things. Gauss law says that the net flux through any closed surface surrounding, this is, by the way, not right, surrounding a charge q, a net charge q, not necessarily a point charge, is given by that net charge divided by epsilon naught, is independent of the shape of that surface. If there is no net charge surrounded or enclosed by that surface, the flux definitely is 0. The electric field at the Gaussian surface that is used to calculate the flux is the vector sum of all the electric fields produced by all sources, whether inside or outside the surface. Okay? This point I will just demonstrate further now, but it's important. That is, on the left-hand side of Gauss law, you have an integral E dot dA. Now, this E there is the field at the surface. This field at the surface can be generated by charges wherever it is. Okay, so and it is the field at the surface. So when you calculate the flux by using that integral, you must take that electric field, okay, whether it's due to charges inside the surface or outside the surface. Okay, but the flux, when you do this calculation and find the flux, what you get is that that flux is equal to the charge inside that surface only divided by epsilon naught. This is what I'm saying, that the electric field here is the electric field contributing from all points. Let's consider, for example, another example, a demo of Gauss law. Here I have a closed surface again, and I have this closed surface doesn't contain any charge. It doesn't enclose any charge, but there is a charge outside that surface. There is a point charge outside that surface. I'm taking it as positive point charge, and I'm showing the electric field lines originating at that positive charge, actually part of them, because, you know, these lines should go in all directions and continue to infinity. But I'm showing only part of them. These are penetrating the Gaussian surface. Now, Gauss law says that the net flux through that surface is equal to 0. Okay? Now we observe the following. Now, if you look here, because I don't have charges inside the surface, and all the flux of electric field lines that is through the surface is coming from outside, from charge outside, then, and because these are continuous, and there is no place where they sink or there is no origin of them, there is no charge here where they originate, then all the number of field lines that are coming is equal to the number of field lines are going out. That is, each line, each electric field line enters the surface at some point but leaves the surface at other points. So the net number of lines through that surface is 0, because, you know, when it enters, you have negative flux. When it leaves, you have positive flux, because each entering lines eventually leaves. Then the net flux, the net number of lines crossing the surface is equal to 0 when I don't have sources or sinks of electric field lines inside the surface. And therefore, this is what Gauss law says the flux through the surface in this case must be 0 if it doesn't include a charge. So this is an explanation of the fact that a demonstration actually, the fact that why, when you don't have charges inside the surface and the electric field lines crossing the surface are due to sources outside that surface, then in this case the flux through that surface is definitely 0, because what comes in goes out. So when we don't have sources or sinks of the electric field lines, sources or sinks of the electric field lines are what? Are the charges enclosed by a surface, then the net flux is 0 simply because what comes in must go out. Okay? The lines that come in must go out. Note that, this is what I wanted to describe. Although the flux through the surface is 0, the electric field at the surface is not 0. Because evidently you have a charge here, and at point here, there is an electric field due to this charge. So having 0 flux through a surface does not necessarily mean that you have a 0 electric field. Okay? This is quite important. Okay? But if you have a 0 electric field on a whole surface, you must have 0 flux. Okay? So 0 flux does not mean, through a closed surface, does not mean 0 electric field, but 0 electric field on a surface definitely means 0 flux. This is something that you have to keep in mind. So this is important. Okay. Go through this checkpoint also before, and let's look at another demo or another example. Here we have 4 charges, 1, 2, 3, 4, and we have 3 surfaces, and we want to see which charge contribute to the flux through which surface. Now let's look at surface 1. Now Gauss law tells me that the flux through this surface now is equal Q enclosed over epsilon naught. What's Q enclosed in this case? It's just Q1. So the net flux through this surface, irrespective of its shape or of its size, is just the charge enclosed by that surface divided by epsilon naught. It encloses only Q1. Now Q1 is negative, therefore this flux is negative here. What does this mean? Why this should be negative? Because well, the charge enclosed by the surface is negative charge, and so the flux is negative. What does this mean? It means that there is a net number of electric field lines entering the surface. A net number of electric field lines entering the surface. This is the meaning of negative flux. Recall our discussion of the flux through a closed surface. It's exactly, if you remember that, then this is exactly what does it mean. So a negative flux through a closed surface means net number of lines crossing that closed surface. If you look at surface S prime, the second surface, then in this case it encloses 2 charges, Q2 and Q3, so the flux through S prime is, which is phi prime, is this. Okay. Now this can be greater than 0, can be less than 0, depending on which one is larger, and if they are equal it can even be 0 in this case. Okay. Now for S prime, this surface, this doesn't enclose any charge, so the net flux through that surface is equal to 0. Okay. So there's no problem. However, the electric field, the Q4 here, does not contribute. It exists here, but does not contribute to the flux through any of these surfaces. Okay, because it's not enclosed by any surface, so it has no role as far as the flux through these surfaces is enclosed. It doesn't contribute to the net flux. Okay. Now, however, you have here to remember that this Q4, just like all the other charges, contribute to the electric field at each of these surfaces. So, for example, consider Q4 in respect to this, in connection with S prime. The field of Q4 is felt by S at the surface of S double prime. But the field lines generated, originating at Q4, enter and leave. And therefore, they do not give a net flux through S prime. But the field at S prime here is not 0. I mean, it has contribution from all the charges. The field here is the superposition of the field of Q4, Q1, Q2, and Q3 at each point on the surface. But because all of these charges are outside the surface, the net electric field here, lines, will be actually coming and going out. Okay? They will not, there's no net number of lines emerging out of the surface or into the surface. That net number of lines happens only when you have sources of sinks of electric field lines enclosed by the surface, like when you have it here or you have it here. Okay? So this is a point that you have to understand.